So, you're using Git every single day, right? Commit, push, pull, everything's humming along just fine. And then, it's not. Suddenly, you've hit the wrong key, made a mistake, and that cozy, familiar workflow just explodes into a late-night panic. You're desperately Googling, just hoping you don't make everything 100 times worse.
Oh yeah, we've all been there. Staring at that blinking cursor, copying and pasting some monster command from Stack Overflow, and literally just closing your eyes and praying it works. It's this universal feeling of dread that every developer knows. That moment the tool you depend on feels like it's turned against you.
And here's the real problem, the uncomfortable truth. Most of us, even developers who've been doing this for years, are kind of just winging it. We've memorized a handful of commands for our daily routine, but we don't really get what's happening under the hood. Our whole understanding is like a house of cards, ready to fall over at the slightest mistake.
Well, that stops today. In this explainer, we are going to fix that. We're going to build a solid, intuitive mental model of how Git actually thinks. The goal is to replace that fear with straight-up confidence, so you can stop memorizing commands and start thinking in graphs.
All right, first things first, I want you to forget almost everything you think you know about commits. At its very core, Git is just a database of snapshots, and the most basic building block is the commit. But here's the twist. A commit is not a list of changes. It's a perfect photograph, a complete snapshot of your entire project at one specific moment in time.
So, every single commit has 3 key ingredients. First, a pointer to that photograph of all your files. Second, the metadata. The basics. Who did it, when they did it, and the commit message explaining why. And third, and this is the absolute key to everything, a pointer to its parent commit. That one little link is what turns a bunch of snapshots into a coherent story, the history of your project. And this chain of commits all pointing to their parents, well, it forms a structure with a super intimidating name, a directed acyclic graph, or a DAG. But don't let the name scare you, it's actually simple. Just think of it like a family tree. It's directed because every commit points backwards to its parent. It's acyclic because there are no loops. You can't be your own grandpa, right? And it's a graph because it's just this whole network of commits and links. That graph, that is your project history.
Okay, so this graph can get pretty big and tangled. So how in the world do we keep track of where we are? How does Git know what we're actually working on? Well, that's where branches and head come into play. And trust me, they are way, way simpler than you think.
So many people think a branch is this big, heavy, separate copy of your entire project. Nope, that is completely wrong. A branch is basically just a sticky note. It's a tiny, tiny file that contains nothing more than the ID number, the hash, of a single commit. That's it. When you make a new commit, Git just peels the sticky note off and moves it to the new commit. It's why creating and switching branches in Git is lightning fast.
So if branches are just sticky notes pointing at commits, how does Git know which sticky note we're looking at right now? Well, that's the job of head. Just think of head as the big "you are here" arrow on a shopping mall map. It's another pointer, and it almost always just points to the branch name, the sticky note that you're currently working on. So when you run git checkout, all you're doing is telling Git, hey, move the "you are here" arrow to point to this other sticky note.
And this brings us to a term that freaks everyone out, the detached head. So what is it? It's what happens when you tell the "you are here" arrow to point directly to a commit, instead to a branch's sticky note. Head is just kind of floating out there on its own. Now, you can still work and make new commits, but there's no branch, no sticky note following along. So the second you check out something else, those new commits become orphaned, totally lost. Eventually, Git's cleanup process will find them and poof, your work is gone for good.
Okay, before we start fixing mistakes, there is one last crucial piece to our mental model. It's the idea that at any given time, your code actually exists in 3 different places or 3 different worlds. Once you get this, you'll understand pretty much every major Git command. Let's follow a change on its journey. When you first edit a file, that change is in your working directory. These are just the files sitting on your computer. When you're ready, you run git add. This moves a copy of that change into the staging area, which is kind of like a waiting room where you prepare your next snapshot. And finally, when you run git commit, Git takes everything in that waiting room, bundles it up, and creates a new permanent snapshot in the repository. Working directory, staging area, repository. Every single change has to follow that exact path. All right, now we have our mental model locked in. We know commits are snapshots, branches are just pointers, and our code moves through 3 distinct worlds. Now we can use this knowledge to tackle some of Git's scariest undo commands without breaking a sweat.
Let's start with git reset. Its main job is simple. Move a branch pointer, that sticky note, back to an older commit. But it has 3 flavors that affect our 3 worlds differently. Reset soft only moves the branch pointer. Your changes stay put in the staging area, all ready for a new commit. Then there's reset-mixed. That's the default. It moves the branch pointer and it empties the staging area, putting your changes back in your working directory. And then there's reset-hard. This one moves the pointer, empties the stage, and it overwrites your actual files. Any uncommitted work is just gone. You got to be really, really careful with this one.
Now, git revert is a totally different beast. It doesn't move pointers around or destroy anything. Instead, it creates a brand new commit that perfectly undoes a previous one. So if an old commit added a line of code, the revert commit will create a new commit that removes that exact same line. This is the safe, polite way to undo changes that you've already shared with your team, because you're not rewriting history, you're just adding to it.
This whole idea of rewriting history brings us to the great developer debate: merge versus rebase. When you want to bring changes from one branch into another, you've got 2 main options. Git merge is all about historical accuracy. It creates a new merge commit that ties the 2 histories together, preserving the messy, parallel reality of what actually happened. Git rebase, on the other hand, is about telling a clean story. It rewrites your history to make it look like you did all your work in a straight, neat line. So, do you want the messy truth or a clean narrative?
But here's the most critical thing to understand about rebase. Git can't actually move commits. Remember, a commit's identity is locked to its parent. So what rebase really does is it takes your commits and one by one, it replays the changes on top of the new base, creating brand new look-alike commits with different parents and different IDs. The old commits get left behind. And that is why you never ever rebase a shared branch. If your teammates base their work on those old commits you just orphaned, you've literally pulled the rug out from under them and chaos will follow.
So, what happens when you mess up? You ran that reset-hard by mistake, you rebased a branch you shouldn't have, it feels like hours of your work just vanished into thin air. Well, don't panic, because Git gives you one last, amazing, get-out-of-jail-free card. I want you to meet your new best friend, Git Reflog. See, Git almost never throws anything away immediately. The reflog is your own private journal that keeps a record of every single move your head pointer has ever made, every checkout, every commit, every single reset. That commit you thought you lost forever with that bad rebase, its ID is almost certainly sitting right there in your reflog, waiting for you. It's your personal time machine to recover from almost any disaster. So let's wrap this all up. Git is just a database of snapshots. Those snapshots point to their parents, which forms a graph. Branches and head, they're just simple, lightweight pointers, sticky notes, and you are here arrows. Checkout moves where you're looking. Reset moves the actual branch. Revert adds a new commit to undo an old one. Rebase rewrites your story by replaying your work. And when it all goes wrong, reflog is your ultimate safety net.
So the next time something goes wrong in Git, you're not going to panic. You're not going to blindly copy and paste from the internet. Instead, you're going to take a breath and visualize the graph in your head. You'll think, where are the pointers? And where do I need them to go? You'll understand what happened, and you'll know exactly how to fix it. You're not just memorizing commands anymore. You're speaking the language of the graph. So with this new Fluency, what will you build?